Let's take a look at this differential equation. We want to find a series solution to this differential equation. That's x squared minus 25, the whole quantity being multiplied by y double prime, plus 2x times y prime plus y. So assuming that we have a series solution, and this is x is equal to 0 as a regular point, our series solution would look like y equals the sum, the series, from n is equal to 0 to infinity of c sub n x to the nth power. To put that into the differential equation, we need our first derivative and our second derivative. And so if we take the first and second derivatives, we have these two new series. And that's a series with n going from 1 to infinity of n c sub n x to the n minus 1. And the derivative of that would be the series starting at n is equal to 2 to infinity, n times n minus 1 times c sub n x to the n minus 2. So what we want to do is take our series and put in our series expressions for the second derivative, the first derivative, and the original y value. So our second derivative is that series that starts off with n equals 2. Our first derivative is that series that starts off with n is equal to 1. And then our y is the original y series that we have. All right. So I will copy and paste and move things around. This series over here gets distributed to the x squared minus 25. So let's go ahead and distribute that and see how we're going to distribute that. We'll start off here with x squared and then a minus 25 times the same series itself. Okay. So that takes care of that step where we distribute. Our next step is to bring in these values into the series. So we have the x squared being multiplied with x raised to the n minus 2, and that's just going to give us x to the nth power. So the x squared gets distributed. We have a minus 25. We can leave that out there, or we can change this as something that we can put inside. It's not going to make much of a difference. It just might help with some bookkeeping. We have 2x here. A constant 2 will just go outside as a constant 2, or go next to the n as a constant 2. But more importantly, this x goes inside to the x to the n minus 1, and so that can go away, and this will just be x to the nth power. The last one didn't have any constants or any other polynomials on the outside, so this is what we have. Okay, now looking at the x to the n's here, we have a few x to the n's. The only thing that's not kind of following the same orders that we have is this term, or this series that has an x to the n minus 2. So that is what we're going to work on. We're going to shift the indices for that. And if you want to make a little note for yourself, we are letting, in this case, k to equal to n plus 2. Or I think that should be n equals k plus 2. So we'll replace everything here with, well, this is going to be n minus 2. This is going to be k. Basically, what we're going to do is we're going to reduce this by 2, or add 2 to it. So we add 2 to this and change the variables k. We add 2 to this. We add 2 to this. And we can simplify k plus, and then we have a 2 minus 1, which is equal to 1. So that's easy enough to do. And then we have k plus 2. So as we do the switches inside, we're going to change our index, and we're going to subtract 2 to the index, the starting index, and we're going to start off with k is equal to 0. So now that we have that, we have matching powers, x to the k. Also, if you want to change this into k, let's go ahead and do that since we're changing things into k, just for the sake of being able to match things up and combine series. So all these changes into k's. All right, now they're all k's. They all have matching x powers. The only thing we need to do at this point is to combine the series, and for us to be able to do that, they need to have the same starting points. Now there's a couple that start at 0, and there's one that starts at 1, and then one starts at 2. So k is equal to 2 is the largest index starting point, and so I think we're going to want to keep that. So meanwhile, we're going to change these series, the ones that don't start with a 2, and then take out a couple of terms. So for this one, when k is equal to 0, we're going to take out this quantity. When k is equal to 0, and the same quantity when k is equal to 1. So k is equal to 0. We have just a 2, this is just a 1, this is just a 2, and then we have k to the 0th power, which is 1. That's going to make this a constant term, but we'll deal with that in a few minutes. K is equal to 1 here, so 1 plus 2, that's going to give us 3. K is equal to 1 here will give us 1 plus 1, it's 2. K equals 1 here. This is going to be c sub 3, and then k equals to 1 here, x to the first power. It's just going to be x, but we'll keep it as x to the first power for now. And so we took out a couple of terms here, the 0th term, the first term, and so the series now starts at 2. Now we got matching series with the first one. Okay, we need to do the same for the next series because it starts at 1. We're going to need to pull the 1 out when k is equal to 1 term, and then make this start at 2. So when k is equal to 1, we have 1 there. This is c sub 1, and this is k or x to the first power. So it looks like we're going to match these x to the first powers here, and then we'll see if there's any more that comes out. So that takes care of this series. This series that used to start with k is equal to 1 now has a series that starts with k is equal to 2 with the k is equal to 1 term pulled out. All right, this last one we're going to have a couple of terms pulled out here. That's going to be c sub 0 x to the 0 power, which is your constant term, and then c sub 1 times x to the 1. That's your linear term, and then we have a plus the rest of the series where the series starts at 2. All right, so we have constant terms, constant term, linear, linear, and linear. Oops, this should be a C. Let's try that again, C. And then the series, the rest of the series. So let's take all the constant terms together. Let me copy and paste this and move things around just by dragging stuff out. So this is our first constant term. Let's take it all the way out in front. We have another constant term here. Let's take that in front also, next to the other constant terms. So now let's take this linear term over here. Let's put that in front. We have another linear term here. Let's put that in front. And then we have one more linear term here. Okay, so the rest that we have here are all series. Let's simplify this. We know that c sub or x to the 0 power is x. We know that this is 1 whenever we have a 1. We can put negative 50 here, but let's keep it at this for now, just in case we might see a pattern. I don't know if we'll see a pattern. X to the 0, that's gone. So these two can get wrapped up together. So let's bracket them. And then now we have x to the first power. That's just x, x to the first power. That's just x, x to the first power. That's just x. There's a 1 here. Let's check that out. So we have a couple of c sub 1s. So there's 2 c sub 1 plus c sub 1 where the x can get factored out. So let's factor out the x. And then 2 c sub 1 plus c sub 1 is just going to be 3 c sub 1. Okay. And again, we have an x term in there. So this is our linear term. Let's take the x out and factor it out. So then this is really what we have. So that's our linear term. All right. So we dealt with the terms that are outside. Now let's take all the terms that are in this series. It's basically taking all these terms. They all have an x in it. So it's like taking all these terms and then just putting it all in one series. So let's attempt to do that. Let's take this term, and I'm going to leave the x out because I'm going to end up factoring that out anyways. So we have that term with the x, so this term is gone. Now we'll take this term and add it on. So plus this term. And so the x is gone again. And then now I'll take this term, which is just c sub x. And the x taken out, so that term's gone. So this is our series. So we have constants and we have this series, and let's just take a look at this series. And there's a c sub k, there's a c sub k and a c sub k, and then there's c sub k plus 2. So we can find a recurring relationship between c sub k and c sub k plus 2. So let's just for the sake of being able to combine it later, let's put the c sub k's together. Let's see if we can maneuver that over here. So we have a c sub k plus 2, and then these terms over here all have a c sub k. So let's wrap them all up in the parentheses. And take out a c sub k. So this c sub k is gone, this c sub k is gone, and this c sub k is also gone, but we have to replace it with a 1, and the c sub k can go outside of that parentheses. So this is what we have for our term. I suppose we can try to simplify that. Let's leave it like that for now, and so we have our equations that we're going to want to deal with. Okay, so let's go ahead and, well, let's just work with it here. This is our first, our constant term. It's supposed to be set equal to 0. And so let's see, how's this going to work out? We want to solve for the sub that's highest, and that's c sub 2. And so we bring the c sub 1 over to the other side. And then we're going to get, we're going to have to divide out by a negative 25 over 2. So c sub 2 will equal to 1 over 25 times 2. I mean, that's 50, right? And the negatives will cancel, and then we have c sub 0. So that's 1 over 50, but let's keep it unmultiplied or simplified or unsimplified for now, and see if there's anything that we can put together in a pattern. All right, our linear term is also going to be set equal to 0. And what is this going to look like? So this looks like we're going to want to solve for c sub 3, and then in terms of c sub 1. So c sub 3 is going to equal to, now we have a negative that goes on the other side, but it's going to cancel with this negative. And then we have a 3, c sub 1. Oops, let's be careful here. 3 c sub 1 divided by these things. Again, the negative was canceled because when we brought that over. And then the c sub 1, we'll keep it out here. Okay. So we have c sub 2 and we have c sub 3 in terms of c sub 0 and c sub 1. So c sub 0 and c sub 1 are probably going to be your arbitrary constants. And then now we have this relationship equal to 0 when for k values that are bigger than or equal to 2. So what we want to say here is that when k is bigger than or equal to 2, we get this relationship equal to 0. So we're going to want to solve for c sub k, or c sub k plus 2. And that's going to equal to some big fraction, right? So what's that big fraction going to equal to? Well, let's put a c sub k on the outside. We know that the c sub k came out. So it's going to be this expression over here with a negative sign divided by this expression over here. But that expression also has a negative sign. So let's cancel out this negative and this negative. And then this is what we have. Well, let's take away the c sub k also. So this is our relationship here. So c sub k plus 2 is equal to this. These are values for values k bigger than 2. So let's figure out how these things are going to look like. So when k is equal to 2, that's our first case. Let's put k is equal to 2 here. 2 plus 2 is 4. We have a 2. 2 minus 1 is 1. 2k is 4. 4 plus 1. We'll figure that out. We have 25. This is 2. 2 plus 2 is 4. 2 plus 1 is 3. And then this is 2. So we got something in terms of c sub 2, which we'll replace with this. And so let's go ahead and do the replacement. Let me just copy and paste this and replace c sub 2 with this expression. All right. So what do we have for the numerator? We have that's 2 plus 4 is 6 plus 1 is 7. So it looks like we're going to have a 7. We have a 25 times 25. Let's call that a 25 squared. And then we have 4 times 3 times 2 times 1. It's not there, but we can just put it there. So that's 4 factorial. Okay, So that's our C sub 4. C sub 4 looks like it's going to be in terms of C sub 0 after we make that replacement. All right, so that's what happens when k is equal to 2. How about when k is equal to 3? Let's take that expression that we have again. This is our relationship when k is bigger than or equal to 2. So we'll put 3 in here. 3 plus 2 is 5. So we have 3. 3 minus 1 is 2. This is times 3. 3 plus 2 is 5. 3 plus 1 is 4. And this is a 3 as well. And so C sub 3, we have a value for C sub 3. That's something in terms of C sub 1. So that's C sub 1. We have this thing expression. Let's see if we can simplify this. We have 6 plus 6 is 12, plus 1 is 13. So we have a 13 times 3 in the numerator. And then let's go ahead and write that out. Uh, 13 times 3, or 3 times 13. And then in the denominator, we have 25 squared again. And then we have 5 times 4 times 3 times 2. So that looks like it's pretty much going to be a 5 factorial. I guess we're good. We have up to C sub 5. Let's maybe do a couple more and see what we can get. So our next one will be when k is equal to 4. And this is our relationship. I'll go ahead and copy and paste and change my k values to 4. So 4 plus 2 is 6. We have 4. 4 minus 1 is 3. 2 times 4. And then we have 6 and 5. And C sub k is equal to 4. What is C sub 4 equal to? C sub 4, we did that one. That became, it was this expression over here, which is 7 times 25 squared times 4 factorial. So this is going to be something with a C sub 0 in it. Our numerator is going to be 7 times, and then we have a 12 plus 8, that's 20, plus 1 is 21. So we have a 21 times 7 in the numerator. We have 25 squared. And there's one other 25 here that we're multiplying, so that's 25 to the 3rd power. And then we have 4 factorial and 6 and 5. So 6 times 5 times 4 times 3 times 2 times 1. So that's essentially 6 factorial. And then here's our expression for C sub 6. Okay, let's do one more. K equals 5. And when k is equal to 5, we're going to have C sub 7. So C sub 7 equals 5. And this is 5 minus 1. That's 4. 2 times 5. And then we have 5 here. 5 plus 2 is 7. 5 plus 1 is 6. and then c sub 5, which we have a value for. C sub 5 was equal to this expression. We'll copy and paste that in a minute. So let's double this up. This is the value for c sub 5 that we found. C sub 5 is 3 times 13 c sub 1 divided by 25 squared plus 5 factorial. So we have something with the c sub 1. We start off with 3 times 13, and then looks like we're going to have something else here, and that's 5 times 4, that's 20, plus 10, plus 1. Looks like it's going to be a 31. So let's go ahead and put that value there, and then we have 25 squared times 25, so that's 25 to the third power. Just copying and pasting here, 25 to the third power, and now we have 7 times 6 times 5 factorial, so that's 5 times 4 times 3 times 2 times 1, and that's just going to end up to be 7 factorial. Okay, so it looks like we're on our way to have at least up to c sub 7. And so what we can do is we can express our solution up to x to the 7th power. Okay, so all we're going to do is literally replace these c sub values here. So let's go ahead and do that. C sub 1 and C sub 0 are up here, and we don't have real values for that. We start off our values with C sub 2. So C sub 2 gets replaced with this expression. C sub 3 is still up here. C sub 3 is this expression here. So we can replace C sub 3 with that expression. C sub 4 C sub 5 C sub 6 oops, let's put that inside of the parentheses, and then finally C sub 7. Now, if you notice, there's C sub 0s that we can factor out, so we're going to regroup that. Let's copy and paste this and do the regrouping. Let's regroup it with a couple of parentheses. Let's try that again. Parentheses plus parentheses. All right, let's put the C sub 0s in there. We have C sub 0 and the C sub 1s. And then C sub 2. And then C sub 3. Oh, we have C sub 4. That has a C naught. The x to the 4th has a C naught. C sub 5. X to the 5th. C sub 6. And then C sub 7. Let's get that plus sign in there. All right, so here we go. We have the expression up on top. Oops. They all have a c sub 1, so except for this one, which can just get replaced with 1. Let's take all the c sub 1s out. Or c sub 0s. And then also this thing has a c sub 1. Let's take that out. And then all the other c sub 1s can go away. And now here goes your expression. Now you can try to find general expressions for this. That would be a good challenge so that you can write it as a sum. And it looks like there's some sort of pattern here. We got x squared, x to the 4th, x to the 6th, so you can call that x to the 2n. The difficult pattern to find is 7 times 21, and whatever the next one might be. And I bet it's going to have something to do with this expression that we have up here. That was a numerator. But the 25s are easy to follow. We got 25 to the 1st, 25 to the 2nd, 25 to the 3rd. And then we have 2 factorial, 4 factorial, 6 factorial. Similarly, we have odd powers. So that's like a 2n minus 1 or 2n plus 1 scenario. That matches with a 7 factorial, and then there's a power of 25. By the way, we can rewrite this as 3 factorial if we want, because that's what it is. And then the numerator, again, that's a trickier one. We got 3, 13, and 31, and again, it should follow with this relationship: the k times k minus 1 plus 2k plus 1. Okay. So this should be your solution. You can multiply things out. I believe this is 50 and whatever this turns out to be, and then these denominators are going to get extremely large, but you can do that multiplication and simplifying so that you get a nice fraction. Okay, so I hope that helps.